Hi guys, let me take you through the results here of the study guide, which is introducing you to significance testing. So when you are doing a significance test, you're looking for evidence against the null hypothesis. The null hypothesis is often written as H with a subscript of O. The hypothesis we expect might be true. This is called the alternative hypothesis. The alternative hypothesis, alternative starts with A, so it's written H sub A. So we seek evidence against the null. We're looking for evidence of the alternative. So an alternative hypothesis can be one or two-sided. A one-sided alternative means we're looking for evidence greater than the null hypothesis value or less than the null hypothesis value. So really one side means one direction. A two-sided alternative, which we will look at tomorrow, is a not equal to alternative. So something to remember, the null hypothesis is always an equation. The null hypothesis is always an equation, and later on we'll see why that's important. Hypotheses are always written using parameters like p or mu. They are not written in terms of statistics. So the hypothesis p hat equals 0.64 or x bar greater than 85, these are wrong because they should be written using population parameters. I don't have to write a hypothesis about a statistic. I know the value of a statistic from the data in the sample. I need to make a hypothesis about the unknown population parameter. So instead of p hat equals 0.64, I would write p equals 0.64. Same thing, instead of x bar, I would write that mu is greater than 85, if that's the hypothesis for which I'm trying to find evidence. So, continuing then, a significance test answers the question, how likely is it to get a sample result like the one that's observed just by chance, just by random chance alone, if the null hypothesis is true, if HO is true? So if you looked at the dot plot on page 542, like we've done before, the true success rate here is 80%. That's the success rate for free throws that we were using in our simulation, because that's the value that's in the middle of the distribution. It's in the center of the distribution. We've talked about that before. The sample proportion is an unbiased statistic. The truth will be in the middle. So sample proportions as small or smaller than the observed p hat of 0.64. They have a probability. In this case, if you look at this, I'm looking at this value again, that probability based on the simulation is only 0.0075. So, but that's assuming that the null hypothesis is true. So understand, if you think the null hypothesis is true, that statistic, or something even more extreme than that, only happens with this likelihood if that 80% is true, if the null hypothesis is true. So either something unlikely has happened, which is unlikely, or maybe the null hypothesis isn't true. Maybe our statistic is giving us evidence that the null hypothesis isn't true. Maybe it's the alternative hypothesis that in fact is true. That's really the basic logic behind significance tests. And that likelihood that we use in order to make our decision is called a p-value. So a p-value is the probability of a sample statistic. So a p-hat or a sample mean, an x bar, as or more extreme. So as extreme or more extreme than the one that's actually observed if we assume that the null hypothesis is true. So because there is a condition here, assuming that the null hypothesis is true, this condition here means that p-values are conditional probabilities. P-values are conditional probabilities. So if you look at the healthy bones example, we're looking for the probability of a sample mean as low or lower than 1,198 milligrams of calcium under the condition that the null hypothesis is true, under the condition that mu, The real population mean is 1,300 milligrams of calcium. So that probability, when you look at that in that context, is 0.1404. So two conclusions then can be made in a significance test by using that p-value. If you have a small p-value, we reject the null hypothesis. And that gives us evidence, not proof. Evidence that supports the alternative hypothesis. So if we have a larger p-value, a larger conditional probability, then we fail to reject the null hypothesis. So in this case, we don't have evidence for the alternative. So notice the nots go together. So failing to reject the null hypothesis, that means that we don't have evidence of the alternative. So the significance level, this is known as the Greek letter alpha. It's the value to which we compare the p-value in order to decide or to determine the conclusion that we can draw. So when the p-value is less than alpha, that's when we say that we have a small p-value. That's when we say something unlikely has happened. So when the p-value is small, specifically when it's less than alpha, we say that we have a statistically significant result. So if you look at the better batteries example, if you look at that example, we were using a level of significance, or one of the things you were doing was using a level of significance of 0.1. So notice here in the better batteries example, the p-value is 0.0729. So if you compare that to the 10% level, our p-value, again, was 0.0729. And the comparison we're going to make is to our level of alpha. That's less than 0.1. So in this case, this result is statistically significant because the p-value is lower than our level of significance. So in this case, our p-value is lower than alpha, our level of significance. We have a statistically significant result. What that means is that we can reject the null hypothesis and we could say that we have evidence of the alternative hypothesis. That's the logic behind significance tests. And it's going to take us a good week or so to really get that logic under control. I just want you to see the basic structure today. So like many things in statistics, our decision boils down to a comparison. We're comparing a p-value to our level of significance to alpha in order to make our decision whether we will reject or not reject the null hypothesis, and that will let us write about our conclusion whether we do or don't have evidence of the alternative. So the most common level of significance that we use is 0.05. That's an alpha level of 0.05. That was first recommended by Sir Ronald Fisher. A little history here. In a paper he published in 1926.